Good afternoon, everybody. Welcome to another exciting afternoon of organic chemistry with your host, me, Dr. White. That's Chem 170 from Elgin Community College. Actually, ECC North, or actually ECC Northeast, really East, because it's my home. But, anyways, good afternoon. All right, important things. One, tomorrow, after lecture, about 4:15, I will be sending out an email with the password for test number 3. You'll have until uh, Friday morning. I think I set it at 11 a.m. or 10. I think it's 11 a.m. to take test number 3 and upload your answers as a PDF file. Make sure I can open it. And also, I would highly recommend that you check that all of the um, pages are readable and that you've answered in your PDF file, you have all your answers. Hold on one second. Fan I have on, I think is causing problems. The fan is off. Let's see. Yep, that was the problem. The wind from the fan or the airflow. But anyways, I shut it off. All right. Remember, get it in on time and make sure you check all the problems are in your PDF file. And I've already talked about what it will cover. Tomorrow, let's see, is Thursday, and from 4 until every couple hours till 9 or 10 o'clock at night, I will be checking my email, and early Friday morning, I'll check it to make sure that if you have any problems, email me. Also, let me remind you, because it's a personal thing I have to take care of today, my office hour at 5. Nope, it will be at 8 o'clock tonight. And if you need any help in any way, stop by. I'll be at my office hour 8 to 9. But if you need a little extra help, I don't have a plane or train or bus to catch, so I'll help you out for a little even afterward. But remember, 8 o'clock tonight. Now, good news. I finally got myself in gear. Well, actually, I've been very busy the last week and a half, and I've caught up with all grading of labs. This morning, I uploaded to D2L all the labs you've done through today. I believe I'm caught up, or I'm not sure if I did. Yeah, I did the carboxylic acid lab. So I'm caught up. Remember, labs are 11 points. If you have any questions ever why I graded a lab a certain way, ask, because there's no such thing as a dumb question in my universe. And with that, I'll ask, are there any questions? I don't know why this is, when I go like this, sometimes I can see it, there, did it again. Well, I don't know what this is, but I've got a backup camera if this one fails. All right, my whiteboard is ready to go. I'm ready to go. Are you ready to go? Let's go. All right, yesterday I was talking about polymer, I did polymers, but I was talking about fats and oils. And fats and oils are triglyceride. And let me just get things. My mouse cable is pushing my mouse where I don't want it to be pushed. All right. I talked about the fact that in general, fats and oils are triglyceride, triester, tri means 3. But for tallow, which is beef fat, you should know, white grease, not named after me, is pig's fat, one grade of it. And another grade of pig's fat is yellow grease. I gave you the following way of writing a good approximation of the real world, which is more fun than this in abstract, which is why I created this. And how can you have a 50-50 mixture of all these contain when you hydrolyze it? Ooh, there should be an O there. Triglyceride and tallow, yellow grease, and white grease are about a 50-50 mixture of saturated and unsaturated. And I taught you that was stearic and oleic acid. So I came up with the idea, how can you have three things 50-50? You can't. Well, then I did this. And essentially, this is our way of drawing any of these three fats. And vegetable oil has more, instead of R sub S, they're mostly R sub O's. But anyways, this is the approximation I'm asking you to use. So let's get back to work. Oh, one other thing. R sub O and the carbonyl is for stearic acid. And you should know the structure of stearic acid. It's got 18 carbons and it's saturated, meaning all carbon-carbon single bonds, all carbon-carbon bonds are single bonds. And this is stearic acid. And this is what I mean by R sub S for this diagram. Now, oleic acid, you should know the structure of, has the following. It's a monounsaturated fatty acid, and fatty acid is a carboxylic acid that comes from fats and oils, and they're always even number, and there's no branching on them. And don't forget, this is material for not test 3, but test 4 coming up soon. It's the fast time of the semester. And this is what I mean by R sub O right here. So if I ask you, draw the structure of stearic and oleic, draw the structure with carbons. If I ask you to use tallow, white grease, or yellow grease, you can use the abbreviation. You don't have to write out all 18 carbons or this carbonyl plus 17 more. Now, I ended yesterday, I was about to talk about saponification. That's the reaction of a fat or oil with a strong base and water. Seaboard. Oh, I've got to get to work. And let me do the following. Let's have some fun, real world fun. And what if I were to ask you, give the product or products for the following reaction? And you look at that and say, how can I react the word with sodium hydroxide and water? But the answer is no. When I say tallow like that, what I really mean is this structure. So as soon as you see tallow, or if I put down white grease, you'd use the same, or yellow grease, you'd use the same. hold on one second. Everybody, did I go through the amine problem set? I'm having a brain freeze. If I didn't, give me a thumbs up. So I did not do it. I thought I didn't do it. Bad, Dr. White. Let me finish this, then I'll go right back and we'll do the problem set. Let me do this one. Thank you. Well, at least I didn't totally forget to do it. That would have been bad. All right, so how do you do this? As soon as you see the word tallow for my class, what I'm really saying is the structure. And if I react this with sodium hydroxide and water, what's the functional groups in here? An ester, 3 of them. And remember, oil chemists write their esters backwards. And hopefully for tomorrow, you know, an ester plus on tomorrow's test, I'll write them like I have been, not backwards like this, but you get the alcohol you would have used to make that ester plus the carboxylate anion you would have used to make that of the carboxylic acid you would have used to make that ester. And I'm going to let you write the products now. It's your turn. There's 3 different products you get there. Even though one you get 2 of, but I count that as only one different product. Why don't you write the products you would get there? I see one person's done, but take your time. Well, give me a thumbs up when you're done so I know you're done. In a classroom, I can just look at the students and I also tell them, I think I said this before, I always say, when you're done, look up and smile, and some do. All right, I think everybody's done, so I better get to work. All right, now, how do you do this? Well, first of all, let's clean up this right here. And we look at ester number 1, and the R group for the alcohol is this. And then this part, what's R prime? R sub S. So you get this carboxylate anion. Second ester, the R group for the alcohol down here I'm talking about, which becomes this, is this, and you get this alcohol. And this part will give me this, which is sodium oleate. This is the top one here is sodium stearate. And finally, the last ester will give me this alcohol, and you get glycerin total. And this part will give me a second one of these. Now, you don't have to put the 2 there because I asked give the organic product or products. I'm not asking you to balance it. So there are technically 3 products. Glycerin, this is called sodium stearate, and this is called sodium oleate. And that's what you get. And I worked for a company that we did similar to this, and that's how you do it. All right. time for Dr. White to go and do what he should have done before doing this. Yeah, Dr. White, not really, just forgot. I was so excited about getting into fats and oils. All right. Could you all give me a thumbs up if you see on your screen amines and amides? Thank you, thank you, and thank you. By the way, my other class at COD, the people don't like doing thumbs up. I don't know why, but they don't. But you guys are fantastic. Thank you. Don't tell them I said that. Shh. But anyways, on test number 3, I'm going to be doing something different. Normally, I ask give the IUPAC name for the following. But for test 3, since for amines I didn't teach you, I showed you, but I really didn't teach you and ask you to learn the IUPAC. Now I will say give the IUPAC or the common name for the following compounds. And you can do either. Now, how do you do it? What's different? Always look for what's different. A nitrogen with carbons on it, it's an amine. How many carbons? You name the R groups on the nitrogen. And this is, and oh, I made a mistake. This 1A should not be butylamine. It should be N-butylamine. Bad, Dr. White. And one specific one you should know is a benzene ring with NH2 is called aniline. If you look at B, I did it right, isopropyl ethylamine, or it could be ethyl isopropyl. Now, I got carried away, cross off D. I will never put that on the test or the final. And if we look at E, we have a quaternary ammonium salt. How do you do that common name? You name each alkyl group as the alkyl group it is, then add the words ammonium halide. And here I have dimethyl and diethyl. It doesn't matter which you put first, then ammonium, and for chlorine, that's a chloride. Now, G is an amine salt, and you name it the same way as a quaternary ammonium salt, but in this case, there's only one R group, N-propyl ammonium chloride. And here I have draw the condensed structures, and for amines and quaternary ammonium salts, I use the common name. And tert-butyl ethylamine, you have a T-butyl group and an ethyl. It doesn't matter which side either is in. Remember, for amines, there's 3 bonds to carbon. For amines, there are 3 bonds to nitrogen, or there can be, for amine salts or quaternary ammonium salts, 4 bonds. For amides, the nitrogen only has, same as amines, 3 bonds. I didn't ask you to learn amides. Now, I got carried away, cross off C, that will never be on there. Ooh, a molecule near and dear to my heart. Ditallow, dimethyl ammonium chloride. And for this, and I taught you, for tallow, which is an 18 carbon group, comes from animal fat, usually pig's fat or beef fat. No, you can still use your fabric softener. Use R sub T, so there are 2 tallow, 2 methyl, and the anion is chloride. E, just cross off, I shouldn't have put there. And methyl tert-butyl, you could do it either way, I was showing you. All right, let's look at some of the problems. But before we do, don't forget placement where you have a bond, one atom bonded to the other. there should be a direct line to it. You shouldn't put it over in left field like some of you did in test 2. So if we look at 1, it's not a factor here, but you have what? Ammonia plus an alkyl halide gives you a primary amine. What's our methyl? Now, let's look at B. This is important. I have methylamine with this. What's different? Carbon, halogen, primary amine, alkyl halide base. You get a secondary amine. The carbon with the halogen is the carbon bond to nitrogen. So it's the center of 3. Let's look at this again. And this attacks and bonds to the carbon with the halogen. So the right answer, and there are many ways I could write it, this would be 1. Remember, there's 3 bonds to nitrogen, and if there isn't, you put in a hydrogen, just like you did with carbon that has 4 bonds. Now I'm going to do it in red, what some of you did, and I'm showing you, see, don't do it, hint, would do something like this. This is wrong. Immediately, this one has 5 bonds. That can't ever be right. This only has 3 bonds to carbon. This is wrong. Make sure whatever you're bonding to new carbon is directly bonded to it, like in here or here. Don't do this. And a number of you did that on test 2 and lost points you should know. Be careful. The way you can tell something's wrong, any structure you write, make sure there's only 4. Yes, 4, 4. 1, 2, 3, 4. 4 bonds to carbon. If there's not, it's wrong, period. I think I might have mentioned the first day or so. If I say I bet, I only say that when I know I won. I don't like to lose. I like to win, but I hate to lose worse. So that's also why I don't go gambling, even though when I go to a crap table years ago at a conference in Reno, Nevada, I did really good. I could usually walk away from a crap table after about 2 hours with at least $2,000 or $3,000 that I won. But I'm not a big gambler, so I've never been to any casinos in the Chicagoland area. They're there, but that's just not in my DNA or blood. But if you have a structure that has less than or more than 4 bonds to carbon, it's going to be wrong. And I'll bet on it. I'll bet all the money into my wallet. And besides my credit cards, I usually carry a couple $50 bills and even sometimes 20s too, a couple hundred or more dollars in my wallet for emergencies. It was like just about everybody else. I can't remember the last time I used paper money to pay for something. You don't anymore, which is all right, but I still carry. And I would bet all that money. Make sure your structures, have 4 bonds to carbon. I got to get that fixed. No, I'm just kidding. All right, let's move on. Now, if you take a tertiary amine, and this is a really, really important reaction because it's near and dear to my heart. This reaction helped pay my mortgage, a couple new cars, got me around various places of the world. If you take a tertiary amine, react it with a alkyl halide, what's different? Carbon with a halogen, tertiary amine alkyl halide base, you make a quaternary ammonium salt. You don't have to show charges, I do, but make sure you have the halide anion present with or without the charge. And since you have two tallow and a methyl, I'm going to add another R triple prime is methyl. This is one way of writing it. There are other ways. Now, if I look at D, I have what? An amine, and it could be primary, secondary, tertiary, an amine with HX, where X is halogen, chlorine, bromine, or iodine, you form an amine salt. And I didn't write a good way of writing the general reaction, so I'll do it again here. Where X can be chlorine, bromine, or iodine. And what you get is this. And remember, R prime and R double prime here can be hydrogen. If we go back to our example, here we have our, I'm about to sneeze, so excuse me, I'm stifling a sneeze. Wants to sneak out, but it doesn't. I think I got, anyways, R is a methyl, and R prime and R double prime are hydrogens. You add a hydrogen from the HCl, and 2 plus 1 is 3, and you have the chloride anion. You don't have to show charges, but make sure you put the chlorine there. It's not bonded covalently, it's an ionic bond to nitrogen, which is different. Most of what we've done is ionic. And here, G cross off, that won't be on test. Now, if we look at H, what do we have? Ooh, a triple bond, carbon, nitrogen, triple bond. And we're reacting with excess hydrogen and a nickel catalyst. What happens? The 2 pi bonds and the triple bond between carbon and nitrogen are broken, and each atom of the triple bond gets 2 hydrogen. Now, I didn't have them sticking up like I normally do. On there, I got, I don't know, lazy. But remember, do you break carbon-carbon single bonds? No. I start with 3. I'm not adding. I better end up with 3 carbons. And on I showed it this way instead of CH2, NH2. I have them. Either way is correct on the test. Now, a benzene ring is very hard to hydrogenate because of aromatic character, and that's why it wasn't touched. And look what I did in J, organic chemistry instructor's favorite trick on a test, big scary molecule. No, it's just an R group, triple bond, break the 2 pi bonds, each atom gets 2 hydrogens. Everything else comes along for the ride. Now, let's look at K. What do we have? A carboxylic acid. What's here? A primary amine. If you take a carboxylic acid and amine, remember R prime and R double prime, both can be hydrogen, like we'll see in ammonia in the next step, and you get an amide plus water. You don't have to put that down because I'm asking for the organic products. So here R is methyl, R prime is methyl, and you get this amide. and our double prime is hydrogen. Now here, ammonia won't react with a benzene ring, but it will react with a carboxylic acid, and R is benzene, and in this case for L, R prime and R double prime are hydrogens, and you get this amide. And I have different ones. Now, when you have an amide and react it with acid and water, this is, I'll teach you later before the end of the semester, which isn't that far away. Where does summer go? Time flies when you're having fun with organic chemistry, at least for me. I hope it does for you. But anyways, amide, if we look at P, what's different? A benzene ring, but a benzene ring will not react with acid and water. But we have a carbonyl with nitrogen stuff on it, and a carbonyl carbon has stuff. Amide, R prime and other R double prime, one or both or none, can be hydrogen. You get back the carboxylic acid you would have used to make that amide, and you don't get the amine. Amines are basic. They react with acid to form the amine salt. So you get the amine salt of the amine you would have used to make that amide. And here R is benzene ring, R prime is methyl, R double prime is hydrogen. Notice here, I have two ways you can write the amine salt. Either one would be correct on a test. Now, if we look at R and S, we have an amide reacting with base and water, base hydrolysis of an amide. And here we have amide, what gives the carboxylate anion of the carboxylic acid you would have used to make that amide. Why? Because the carboxylic acid that's initially formed reacts with the base to form the carboxylate anion. But you also get back the amine you would have used to make that amide. Remember, R prime and R double prime, either one or both, can be hydrogen. And if we go to the more interesting S, here, R is benzene ring, so you get sodium benzoate. R prime is methyl, R double prime is hydrogen, plus you add one more. 1 plus 1 is 2 hydrogens, 1 methyl on nitrogen. And same thing with T. Now, there will be some synthesis problems on test number 3. And if we look here, what two products do you react with base to make this compound? Well, it's a secondary amine, and you take an alkyl halide and react it with a primary amine. And I could say the methyl group is R, the ethyl group is R prime, and then this top would be what you got. Or I could say the ethyl group is R, and the methyl group is R prime, and the bottom. Now, since I don't show you a halogen, you can pick any halogen you want for X. Now, on B, we have making a quaternary ammonium salt. And what do you have? You have a tertiary amine plus an alkyl halide makes a quaternary ammonium salt. And I apologize because the anion X minus disappeared. Oh, sorry. Anyways, notice in the product in the question, I have chloride anion, so that means X here is chlorine. And there's two possibilities. One where two of these is R prime, R and R prime. The other on this side is R double prime and also R triple prime, or vice versa. And that's why there's two there. And finally, oh, not finally, if we have something reacting with hydrogen gas, excess and nickel catalyst to form, what is this, a primary amine. How do you form a primary amine? Nitrile hydrogen excess catalyst, which can be nickel, platinum, or palladium. Now, are we adding carbons here? No. So therefore, it's time to use common sense. But every time I say that, one of the great mentors, and I like to think about him because he sure was really great for me. When I started out in the chemical industry, I had a mentor, Mr. Sid Shapiro, and Sid was my mentor. He was about, at that time, 40 years older than I was. He was near the end of near retirement. He was already in his late 60s, early 70s. And here I am, a young PhD coming out. But he took me under his wing. And then he would always tell me, remember, common sense is common. That's how he talked. And he'd say, remember, common sense is common, Sonny. I look at him and say, thank you, but you're not my father. Don't call me Sonny. And we both laugh when I'd say that. And he'd still call me Sonny. But common sense is not common, but it's time to use some. And if you look at this reaction, how do you know what to start with or check you did it right? You're not adding any carbons, and you don't break carbon-carbon single bonds. I ended up with 3 carbons. I better start with 3 carbons, and I do. Now in D, what molecule do you react with HCl and water to get a carboxylic acid plus an amine salt? That's what this is. And the answer is an amide. And you can see how I parsed it. This is our prime, and one of the hydrogens are double prime. And this would be our amide. And now if you react something with base and water, and you get not the carboxylic acid, but the carboxylate anion you see here, but an amine, well, what do you react with base and water to get a carboxylate anion, an amine? The answer is an amide. And here R is this, our prime is this, our double prime is one of the hydrogens, and you get this amide. Did any of you happen to pick up a bottle of vinegar and think, ooh, look, vinegar. It has acetic acid, a carboxylic acid? Did you happen to pick up, what would be another one? A bottle of nail polish remover and look at the label and it says ethyl acetate, and that's an ester. Nail polish remover. You see, I forgot to polish my nail. I'll never be a hand model on TV. But anyways, remember those things. Chemistry is organic chemistry is all around you. And it won't hurt for you to think about that. By the way, I stole that from SpongeBob when he does the one, imagination. Except when he does that, there's a rainbow. I don't get a rainbow. All right, any questions on the amines, amides problem set? Know something? This would be a good time to take a break. It's 1:40. See me at 1:45, or as they say, 1:45, and I'll see you in 5 minutes. Time for a break. Time to get going. All right, let's get back. First of all, any questions about anything about test number 3 tomorrow? I'm looking and listening. All right, well, in that case, let's get back to fats and oils. Now, again, whenever I say tallow, white grease or yellow grease, this is a structure you should use, this triglyceride. Remember, R sub S stands for this. Actually, it's 17 carbons, 18 plus the carbonyl carbon to make stearic acid if it's saponified or acid hydrolysis. We have here, this would give R sub O, which has a double bond in here. And when you hydrolyze this with acid hydrolysis, you would get oleic acid. Now, finally, you get it here the way I have it. In real life, you get a 50-50 mixture because there's more complex mixing going on. But to simplify it, and this is close enough to real life, you get another stearic. So really you get R sub S plus the carbonyls, again, this right here. And I showed you, this is one example. In case you forgot, hopefully not for tomorrow, because you know it the other way. Acid hydrolysis of an ester gives you the alcohol you would have used to make that ester plus the carboxylic acid you would have used to make that ester. And now give me the product. If you react yellow grease with water and acid, what do you get? Your turn. For those who forgot, hint, 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 right here. Well, some of you are done. I'll give you a little more time. All right, let's get to work. As soon as you see yellow grease, white grease, or tallow, remember tallow, beef fat, yellow, white grease, pig's fat, you should write the structure that's my approximation of the real world. And since I worked in this industry, I should know. You would hope so. You have a triglyceride. And we're reacting with acid and water. And I could have put here HCl because that's the acid in your stomach, but I didn't. I put H plus like you've seen all semester. And I have 1, 2, 3 esters, which will undergo this reaction. The first ester, my R group, is this, so I'll get this alcohol, but it's bonded to something else. Remember, you do not break carbon-carbon single bonds. Then my R prime is R sub S. So I'll get stearic acid. And this problem I ask, give all the organic products. Second R group of the second ester is this. So I'll get this alcohol. And the R prime here from this general reaction is R sub. Oh, by the way, you don't have to put the plus signs, but I do. And that means and in a balance or a chemical equation. And I get oleic acid. And the third ester, my R group in the up here is CH2. Then I'll get this, but this part will give me stearic acid again. So I'm done. What do you get? Glycerin, stearic acid, and oleic acid. Like I said, we did this with steam, not with acid and water, to the tune of about 2 to 3 million pounds a week. And that's how you do it. All right. Now let's talk about hydrogenation. And you know, a double bond, but before I do that, let me get a thumbs up for everybody. How many of you have heard of hydrogenated fats and oils? I see one person has. Anybody else? You haven't? Well, they're in our daily life, and medical science has told us they're bad for our heart. Well, I'm not going to get into why they're bad. Let's just believe medical science. I do. But what's happening? Well, see, bored, I've got to get to work. Now, you learned earlier that if you take a double bond, react it with hydrogen and a catalyst, and a catalyst can be nickel, platinum, or palladium, you break the pi bond, and each atom of the double bond gets a hydrogen. Now, let's do the following. Oops, extra hydrogen. Unwhoops. Oleic acid. And let me ask you to do this one. I will tell you, hydrogen and catalyst will not react with a carboxylic acid. So why don't you try what would be the product or product for the following reaction? Remember, you don't break carbon-carbon single bonds. And if something doesn't react a certain part of a molecule, it doesn't change. All right, I think everybody's done. What do we have here? Ooh, a double bond, because this is not going to react. And we know a double bond, hydrogen, and a catalyst, where the catalyst, it can be nickel, platinum, or palladium. You break the pi bond and each carbon gets a hydrogen. So do I break carbon-carbon single bonds? No. The only carbons that are going to change are the double bond. So everything else I can rewrite, and I will. I'm going to break the pi bond. Each one gets a hydrogen. I'm not done yet. I have CH2, 7, and OH. Now, if you notice, this carbon has really CH2, and same thing here, CH2. So how many CH2s in this molecule we just made? 7 plus 2, that's 16. And I could redraw this molecule like this. And we started with oleic acid. And what did we finish up? What's that? Stearic acid. So if you have oleic acid, you can convert it into stearic acid. Let's do a couple more. Why don't you do this one? React that molecule with hydrogen and catalyst. Uh-oh, I see a lot of question marks on people's foreheads. You didn't know I could see your foreheads even with your webcam off. No, I can't. I'm just lying. Kidding, really. All right, let's go back and look at this because I better show you how to do this. What did I say in oleic acid? This is R sub O. What did I say in stearic acid? What is this? R sub S. So the answer to this problem would be this. When we got rid of hydrogenated, the double bond, and got rid of it to make this, R sub O becomes R sub S. And this has a carbon-carbon double bond in that R group. This has none. That's how it happens when you hydrogenate it. Now, let's do the big grand finale. Well, let's do it this way. If you have olive oil or vegetable oil, most of the R groups are oleal. And just in case you have more than one double bond, let's use excess. That means you have all the hydrogen in the world that react anything hydrogen will react with. All right, your turn. What would be the product there? Now notice I have an ester here, here. Let me rewrite this. And instead of writing it, I'll tell you, esters do not react with hydrogen in a catalyst. under these conditions. Esters do not react with hydrogen and catalyst. Double bonds do. Your turn. And all right, anybody need more time, or better yet, if you want me to go ahead and do this, give me a thumbs up. All right, by popular demand, I'll help. All right, hydrogen will not react with an ester. So immediately I can do this. However, hydrogen will react with a double bond. And R sub O, as you can see up here, has a double bond, whether it's attached to a carboxylic acid in oleic acid, or if it's in an ester in a fat and oil. Mainly this would be an oil. And therefore, R sub O becomes R sub S. R sub O becomes R sub S. Will a carbon-carbon single bond react with hydrogen and catalyst? No. So this stays the same. And this is what you get with a hydrogenated fat or oil, mainly an oil because they're cheaper. And why do they do that? Well, it turns out when you have these R groups being saturated as opposed to unsaturated, they are a solid and semi-solid. And for many years, what did certain companies do? They took very cheap vegetable oil, hydrogenated it to make R sub O, R sub S, and now you have a product that's a solid or semi-solid. If I mix it with some yellow pigment, some flavoring, and some water, we call that margarine. And I can sell it for a lot of money and make a lot of money. And they did. It's bad for your heart, but it's good for their wallet or their profits. And they did. And they've changed margarine a little, but anyways, even butter is bad for you too much. But no, garlic butter on French toast, garlic bread, never mind. But anyways, that's why they do it. And a company I worked for, where we made oleic and stearic acid, they also did hydrogenation of vegetable oil to make margarine, and that's Unilever. And one of their products was, I can't believe it's butter, which was very lucrative for them, and I think still is. Uh-oh. Uh-oh. It's time for me to teach you probably one of the most important things I can teach you this semester, and that's how to get clean. Yep, that's organic chemistry. And look out, it's show and tell time. Soap, dial soap. And can you see the label? No, but I'll show it to you. This, I don't like liquid soap in my shower. I use, this is my favorite. Smells good too. Oh, I'm smelling a perfume. That must be an ester. Oh, by the way, did anybody think about fabric softeners or quaternary ammonium salts? Trying to find where I can. Huh. All right, this is the best I can do. Let me make sure you can see it. Does everybody see where it says soap and it says sodium tallowate? All right, and I'll read it in case you can, because it's on the label here too. It says sodium tallowate, sodium palmitate, sodium cocoate, sodium palm kernelate, aqua, which is water, coconut oil, palm oil, acid, tallow acid, glycerin, PEG-6 methyl ether, and fragrance, and sodium chloride and sodium pentasodium, pentanate, tetrasodium, those are, and titanium dioxide. I'm not going to go through all of it, but the key ingredient is sodium tallowate. What's that? Well, you know, sodium and an ATE ending or OAT ending tells you that's a carboxylate anion. And that's the tallow, the sodium salt from tallow, the fatty acids you get from tallow, stearic and oleic. And you also get some sodium palmitate and sodium cocoate, smaller chain ones. They use other vegetable oils too, but mainly soap is the carboxylate anion from the base hydrolysis of animal fat. Not to gross you out, but I will. Did you think of if you use soap, bar soap, the material in here comes from cows and pigs. But by the time you get it so purified, it's not really that, but that's where it started out. I love that smell. But anyways, let's look at how soap works. How do you get clean? Now, when we talk about soap, soap is a certain type of molecule, mainly organic molecule, that we call a surface active agent. And since organic chemists are lazy, I'm not going to say surface active agent, it's been shortened to surfactants. And I worked in 2 companies, actually 3 companies that made surfactants. And they're all different types of surfactants. Quaternary ammonium salt is considered a surfactant, the softener. But we're going to talk about a special surfactant called soap. But before I do that, I need to do this. You should know this. Now, what is soap? Soap is something that has a hydrocarbon tail, which we call lipophilic. Lipo meaning, and I'll teach you about this, nonpolar and philic loving, and has a polar head, which is called hydrophilic, hydro water, which is polar, philic loving. And the key to the puzzle is light dissolves light. And I put a note to myself, remember, light dissolves light. So let's get to work. This is probably one of the most important things I'll teach you this semester. You should know this. And you should be able to describe how does soap work. First, you should know, oops, I got the wrong color pen going. Now I got the right one. What's the structure, one structure of soap or general structure? and that's a nonpolar tail and a polar head. And that both your liquid soap and your bar soap, in general, that's what you're using. Now for bar soap, the polar tail is something like R sub O or R sub S, which you know is 17 carbons. And then the polar head is the carboxylate anion. This is long, 17 carbons, and then this part, because it has a charge here, is the polar head. Now, an important part of the puzzle that you need to know is the rule of thumb, like, hold on. This is the most important piece of the puzzle. Where did you go? There you go. Ah. It's so important. I'm going large font. And what is like dissolve like? Polar things are soluble in polar things. Non-polar things are soluble in non-polar things. You mix polar and non-polar, they're not soluble. So what are polar things? Well, let's take a look. The most polar substance on our planet is water. Alcohols are polar, shorter chain mainly, and salts are polar. What are non-polar? Well, for this one, dirt is non-polar. Grease is non-polar. Oh, some other things just to throw it in. Vaseline is non-polar. Vegetable oil is non-polar. If you take water and vegetable oil, vinaigrette, it separates. But if you take alcohol and water, it's quite soluble. So if you have something, what do you use mainly to clean things with? Water. But water isn't going to touch dirt or grease because water's polar. Dirt and grease are non-polar. Like dissolves like says, they're not going to mix together. They're not soluble. They're not miscible. So what do? Well, let's look at a little piece of dirt magnified. Let's assume on my hand there's a little piece of dirt and I want to wash my hands and get my hands clean. So what do? Well, let's look at that dirt. And you should know this. Here's my magnified piece of dirt. It's non-polar. Water looks at that and says, I'm polar, you're non-polar. I know like dissolves like. I want no part of you. But if you use soap and water, now the soap molecules have non-polar tail and a polar head. And the non-polar tail looks at dirt and says, oh, I'm attracted to you. And the polar head says, I'm not, I'm going to stay away. And it does this with a lot of molecules. I'm just going to do a few. I'll show you a picture in a second. And it forms this new thing. And this new thing is called a micelle. And you should know what is a micelle. It's the dirt particles surrounded by soap molecules. like this. Now, let me show you from our textbook, for those who are reading the textbook, a micelle, which is a small spherical. Not all micelles have to be spherical, but for soap, it is. And here, if you cut out part of the molecule, soap molecules, you can see right in the center there, you have the piece of dirt where all the tails come through, and they're surrounding it. And if you didn't cut it out, this part would be filled like this. And you see the lines, that's the nonpolar tail. And the outside with these like minus charges, that's the polar part of the carboxylate anion, or other types of soaps, the anion polar head. And these are called micelles. And now, water looks at the micelle and says, oh, micelle. And all it sees are the polar heads, because that's on the outside surrounding the dirt, and says, micelle, I'm polar, you're polar, let's go down the drain together. And that's how you get your hands and anything else clean. It works when you're doing your dishes. It works when you're doing your laundry. It works when you're doing your washing your car. You're forming micelles. And not to be too personal, but this morning when I was taking my morning shower, I was thinking, you know something, I'm probably the only person in my neighborhood or my whole city, I live in Schaumburg, who's thinking right now, I'm making micelles to get any dirt off me so I'm nice and clean, fresh and clean for my class today. And that's how soap works, and you should know it. You should be able to describe what is a soap molecule, how does it interact with dirt. You should also know what's the most important part of how do you get your hands clean, or how does soap work, and that's like dissolves like. By the way, like dissolves not like is not a law. A law is always true. Like dissolve like is a rule of thumb. Oh wait, it's written on this thumb today. Bad joke. Sorry. But anyways, it's true usually about 95 or 96%, maybe an higher percent, but it's not always true. There are exceptions. But for soap, that's how it works. And let's go through it again because you should know this. Soap, you should know the structure. Well, where'd it go? Now, let me write it again. When I was an undergrad, when a grad student, if I was taking notes in my notebook and the left margin was real important, I'd put a couple stars. If it was really, really important, I felt, I would put a couple stars and IMP and an arrow. Know this. And I'm writing that so you know this is important. All right, what's the structure of soap? Soap has a nonpolar tail and a polar head. The most important thing of how soap works is like dissolves like. This you should know. That's the most important part of the puzzle. That's why I wrote it in super large letters. I guess those are super large. I'll have to ask Superman about, oh, bad joke, totally bad joke. I'll never, and you should know water is polar, dirt and grease are nonpolar, and like dissolve like tells us they won't be soluble. So how do we get around that? We use soap with the nonpolar tail, polar head. The dirt is nonpolar, the nonpolar tail is nonpolar, like dissolves like. The nonpolar tail is attracted to dirt, and you should know that forms a micelle, and the micelle now attracts water because the micelle water only sees the polar head around the micelle and says, Hey, let's go down the drain together. And that's how you get it. Now, about 4 or 5 years ago, maybe give or take a year, one of my Chem 170 students, a woman, came up to me and said, "Do you hear about this new product called micellar water?" I said, "No." And so she brought me in a magazine with the ad in it. And now it's becoming quite popular. Now, the product itself, which I don't use because very helpful for taking makeup and other things off. As you can see, I use a lot of makeup. But anyways, uh, it's very popular for women. I don't know about men buying. My friends don't use makeup, but anyways, older generation. That's not what I want. If you see right on the screen right now, there are a bunch of products. Now everybody's making micellar cleaning water, micellar cleansing water with vitamins. Oh, I forgot to tell you what vitamins are. If you look at it, it's got water, the hexylene glycol helps sodium. This next thing is this is so a different one, some other stuff. And I've been told it's a very good product, but guess what? There's no micelles in micellar water. What? Yep, no. It's only when you put it on your face and use it, and with the dirt or grease or other things on your face or your makeup, which has a hydrocarbon nonpolar base to it, guess what? Then you form micelles. Like I said, I've been told those are very good products. I don't use them myself personally, so I just don't have the need for it. This stuff works good enough. Sort of like they're saying, "Oh, micellar bars. Ooh, don't. I'm going to sell that." And they command a nice price and are making good profits. All right, let's get back to organic chemistry. So that's how soap works. Now, for this slide switches off. For laundry detergent, they use what's called LAS, linear alkyl sulfonase, and there the structure is this, and this came about after World War, and I've got this wrong. Remember how you learned how to put a sulfonic acid group? You take the proton off there and make it a sulfonate group. Here's my polar head. And it switches off. And here, R is usually 9 to 12 carbons. Here's my nonpolar tail. And this is the laundry detergent, whether I use all myself personally, whether you use all, Tide, or anything. This is the key molecule that cleans your clothes. They have other things in there that helps with it, but this is the main molecule. All right, I'm going to turn the switch. Will this be on a test in the off position? But I thought I'd go through something really quick. There's a group of chemicals called phosphoacylglycerols, which are really triesters of glycerol or glycerin, where two of them are fatty acids. One is called esterified phosphoric acid amino alcohol. And they're also known as phospholipids. And phospholipids have this structure, and again, switches off. And I'm going to draw it a little differently to highlight something. And this is a typical phospholipid. And if we look at this part, with R being either sterile or allele or tallow, mixture of those, this is going to be a nonpolar tail. And this is a polar head. And like the other surfactants, this will interact with many things. Now, one area where phospholipids is important or found, where do you find them? Well, they're also called lecithins, which are really phospholipids, and they're found in soybeans and egg yolks. Now, if you've ever made mayonnaise or see someone, the basic recipe is an egg or really an egg yolk, water, and vegetable oil. Well, wait a second, Dr. White, you said water and vegetable oil are not soluble, like dissolves like. Well, if you use a surfactant, it helps bring the two together, just like dirt and water are brought together with soap. Not that I'd use soap to make mayonnaise, but anyways, you mix these together and you get mayonnaise. And that's using phospholipids. Now, phospholipids are there are a lot of them in soybeans. And you also hear the name edamame. And I buy the green ones that are frozen, that are shelled, and you boil them 5 minutes and I freeze them and you put them in anything. And I found years ago that when I eat enough edamame, not so much tofu does it for me, but edamame, soybeans, it helps my brain work better and I feel better, I sleep better because the phospholipids, lecithin, will affect your brain, at least does mine. And I sometimes get away from eating not enough soybeans. Now I'm getting back into it again and I sleep better and I think better. That's this personal thing. Various chemicals have amazing effects in your body. All right. How are we doing on time? We're doing good. Now, long ago, how long ago? Let's go to the beginning of this chapter. We talked about lipids. Those are molecules that come from plants and oils that are not soluble in water. And we talked about saponifiable lipids, which are really fats. Switches on now. Fats and oils. What about non-saponifiable lipids? Well, guess what? We have a name for those, and that is steroids. Non-saponifiable lipids are steroids, and you also know them as hormones. Now, all the steroids are based on this four-member fused ring. If you notice here, I have a six-membered ring, I'll call it A, attached to another one, B, up here is C, and then a five-membered ring, D. All your steroids, all your hormones have that ring structure. Listen carefully. You should know how to draw the ring skeleton of a steroid. Let me show you how to draw it. All steroids have the following structure: a ring of 6 carbons. Next door is a fused ring sharing 2 carbons. Up here, starting at noon, you have another 6-membered ring. And then next door, you have a 5-membered ring. Not bad. I'm having a good ring drawing day. And this is the ring skeleton for us. I think I spelled skeleton right. If not, you can laugh. And that you should know how to draw. Let's do it again. 6-membered ring. Next door at these 2 carbons is another 6-membered ring sharing those. Then at 12 o'clock high, I have the start of another 6-member ring, not as good as the first one. Then next door, I have a 5-member ring. And you should know how to draw it. Let's do it again. So you have A ring is 6, B ring is 6 over here, not down here, 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 up here. C ring is 6, and then the D ring is 5. And you should know how to do that, how to draw it. Everybody get the message? Just in case. Know how to draw that. Now, give me a second or two. Actually, more. I always spell this wrong. Be with you in a short bit. All right, switch is off, but I thought I'd teach you something. And I'm going to talk about stuff, and I am in no way taking a moralistic stance. This is organic chemistry. Does everybody see on your screen the Wikipedia testosterone, the word? Thank you. Now, if I click like this, here is the structure of testosterone, which is a male hormone. If you look at this, every bend in a line is a carbon and every end in a line is a carbon. Now, these dotted wedges, we'll learn a little about it next chapter, but this shows stereochemistry, whether they're above or below the ring. And these 2 wedges right here are methyl groups. And notice in testosterone, you have this 4 rings, A, B, C, and D. That's the 6, 6, 6, 5 ring skeleton. In ring A, you have a ketone plus a double bond, and in ring D, you have an alcohol. You learned about this. How this does what it does in my body or male hormone, I have no idea, but I'm an organic chemist. I understand the structure and the functional groups. Now, let's look at a female hormone, and that's progesterone. And this is one of the female hormones. And if we look, we have the same ring skeleton. I don't know why something's going on with my glasses, but anyways, we have the same ring skeleton, 6, 6, 6, 6, 5. You have a ketone in ring A with a double bond, but now the difference in a male hormone right here, you have an alcohol, and here you have a ketone, because the end of the line is the methyl group carbonyl carbon ketone. Now, testosterone in the D ring has an alcohol. Progesterone in the D ring has a ketone. Doesn't that make sense? The difference between men and women? Men are alcohols and women are ketones. Never mind. It's totally bad humor Wednesday. Now, what I'm going to talk about the actual implications and no way moralistic stance on it. And that is the following. This is estradiol. Estradiol, it's a common name, not the IUPAC, is a hormone. This is the key female hormone that controls a woman's menstrual cycle. And yes, it's different than the other two I showed you. Notice you got a benzene ring in ring A and a hydroxyl group on it. So this is a phenolic compound. And in ring D, you have also an alcohol. Now, this controls your menstrual cycle if you're a woman, and the amount, how much is in your body affects how your body interacts during your cycle, menstrual cycle. Now, this is very expensive to make, and organic chemists, along with medical doctors, found an interesting thing. And that is, if you look at this carbon in a 5-membered ring, is an alcohol. If you take another cheap molecule and react it with a Grignard-like reagent, a triple bond, this is called an ethynyl group. The ketone here makes an alcohol. This molecule called ethynyl estradiol, your body, if you're a woman, I guess a man too, but a man doesn't have menstrual cycle, your body can't tell the difference. This is inexpensive to make compared to estradiol. And this is the key ingredient in birth control pills. By adjusting over a 30-day period or 31, I don't know, I don't take them, but 30-day monthly period, the pills you take have different levels of this molecule, this steroid hormone in it, which can be made artificially cheap, and that stops your body from getting pregnant, because your body is told what to do and have your menstrual cycle by the amount of molecules in your body, which you take by the pill. And because it was made cheaply, birth control pills were affordable by everybody who wants to buy them. If you had to pay $150, $200 a pill for a birth control pill, how many women would be able to use it? And again, I'm not taking a moralistic view. Not many, but because organic chemists found a way of taking it by something like a Grignard reaction and making that last molecule cheap and finding out with the help of medical science that a woman's body can't tell the difference. That's how birth control pills happen. And with that, I've ended a chapter for fats and oils or lipids and detergents. Don't forget, I'll cover it again. Remember how soap works, like dissolves like. Let's take a 5-minute break. We'll do the lab. I'll get you out in about 20, 25 minutes or less, and we'll be done for today. Don't forget, office hours tonight are from 8 to 9, only tonight. The rest of the time is from 5 to 6. And with that, let's take a 5-minute break, and I'll see you at, let's make it 2:50. Take a couple more minutes than 5. I'll see you in about a couple minutes at 2:50. Time to get going. Let me close a few things here. All right, it's lab time. And let's talk about today's lab. Everybody see it on your screen right now, polymers? Thank you. Now, polymers, as I talked about yesterday, are very large molecules. They play an important part in our life. My water bottle is a polymer. My glass lenses are polymers. And the word polymer comes from the word poly, meaning many, and mer, meaning single unit. These are large molecules with repeating units. Now, in today's lab, and this is a sad day because you'd have so much fun if you were doing it hands-on, but I made a decision this semester. Do I want you to come into the lab, or more importantly, do I want me to, or do we do it this way? And I think with COVID-19 going where it looks better, but I don't know, this is a safer way. Plus, it cuts down on the driving, which is good too. So we're going to talk about a couple different polymers you would have made if we were in the lab. The first one is a urethane or polyurethane. Now, a urethane is an isocyanate plus an alcohol to make a urethane functional group, which you see on the screen. Now, with a polymer, you use a more than one functional group in a molecule. And when you make a polyurethane, you use a diisocyanate reacting with a polyol. Poly, many, OL, alcohol. It's one, a molecule that has many alcohol functions in it. And when you do this, you react it and make a polyurethane. Now, this is a very exothermic reaction. If we were in the lab, you'd prove if I was lying to you or not. I'm not. And because of this, when you have a low boiling liquid in the reaction mixture, it expands and it forms a foam. A foam is just something, a solid with bubbles in it. And I bet you never thought about this, but how many of you have ever seen real bread from a bakery? Not the Wonder Bread, not that there's anything wrong with Wonder Bread, but really good bakery bread. If you cut into it and look at the slice of bread, by the way, I never have them cut it because I have a bread knife and I know how to cut bread. You'll see these little bubble or holes in there. That's because bread is really a foam. When you cook it, the yeast, which forms when it, before you cook it in the dough, you put yeast and sugar, and the yeast eats the sugar, and a byproduct is carbon dioxide, and that causes it to go like this with bubbles in it, and it bakes, and that's how you get a bread. There's more to it than that, but well, foam is simpler. That's similar to it. Now, I have worked in this industry. I have patents in the urethane, so I know it quite well. Now, first of all, let me go to the whiteboard. And in a classroom, I'd be doing this right now. When you make a polyurethane foam, to make it easy, because most of there are two, first of all, there's two main uses. Flexible foam is like for your seat cushions and pillows. Next time you get into a car or sit on a couch, the foam is flexible urethane foam. Then there's a rigid foam. And if you remember the thing I showed you yesterday, that cup that was floating in the air, that's a rigid foam, urethane foam. And that's mainly used for insulation. What? Like your home, or how many of you have ever seen a refrigerator from the 1940s or 50s? The walls are thick. Why? Because they're using glass wool, like the Pink Panther type stuff, to insulate the inner box that's cold from the outside. Well, urethane foam is one of the best insulators around, and it's very thin. And if you look at your refrigerator in your house, if it's not from the 1940s or 50s, between the inner box where you have the food and the outer wall, it's not that thick. It's not like this. And that's because urethane foam makes a very good insulator. That's solid urethane foam. Now, to make it easy to use, especially if you're doing it on a house construction site, the urethane industry came up with a really great idea. They had two different sides or mixed fluids or substances or mixtures, and one was called the A side. And you should know the A side just has the isocyanate. Now the B side has, first of all, the polyol. That's what helps make the, it also has a catalyst, the tertiary amine catalyst. And it has a blowing agent. That's what heats up and makes the foam. And it usually has a silicone surfactant to help make the foam bubbles circular and insulate better. And what you do is you take the B side equal amount and pour it into the A side, mix it well, and you get your foam. Now, when you get the foam, isocyanate, especially for insulation, is a polymeric, and it's almost a black color because you're not going to see insulation. You don't care what color it is. And the B side is sort of a honey color, a light reddish brown. Now, when you pour the B side into the A side and mix it, when the reaction starts, when you're actually starting to make urethane molecules or polymers, the inside looks like turns a cream color, or more specifically, like you put cream into coffee, black coffee. Dr. White doesn't like black coffee, but I've seen people do it, and that's what it looks like. And because of that, urethane chemists came up with a measurement called cream time. And you should know this for the lab. And that's when the reaction starts. Next, when it's rising, making the actual foam, and I'll show you a video in a second, the urethane is sticky, tacky. But if you're doing it in certain plants, they make it in molds to make board stock for insulation for homes. You want to know when you can take it out of the mold. So important thing to measure is the tack free time. And this is one I think I'm spelling tacky right, or sticky. And you can feel that with a tongue depressor. When you touch it, does it stick to it or not? And this happens in seconds. This happens depending on your formulation in minutes. And in the lab, we would measure that. And what you do is weigh out an equal amount of A and B in a plastic container, a cup. You weigh out the A, then in a beaker, you weigh out the B, and you mix the two together and stir and watch. And after it starts rising, I ask students to feel the outside of the cup. If it's hot, that means there was an exotherm. And by the way, it is hot if you look at the data. Let's go back to the lab. And here I have the procedure, how to do it. And let's go to YouTube. Everything's on YouTube except I think my high school, college, and PhD graduation. Everything else is there. Uh-oh, we got stuck with a commercial.
Hi everyone, my name is Kathy Bowie. I am the Materials Products Manager here at Form Labs. I manage.
Goodbye.
Today we're going to talk about molding foam. Specifically today we have a 3 pound per cubic foot molding foam that we want to discuss some of its attributes. This material starts its life off as thin liquids. It's going to be mixed at a 1-to-1 volume measurement, and then it's going to expand. It's going to expand to form a very lightweight foam. And as we said, in this case, it's a 3 pound per cubic foot density foam. So it's going to expand 24 times its liquid volume to create a lightweight, non-absorbing.
See on the bottles, they have A and B. When they sell drums of this to companies, they have been labeled A and B with also ingredients, but anyways.
Closed cell foam that can be easily sanded, or for this demonstration, we're just going to do a free rise bottom of the spatula, not a round dowel, and we're going to pour one into the other, and we're going to simply mix. And it's important that you measure out part B, and now we're going to measure out part A.
See how the A side is very dark? That's the isoside.
And then we're going to take a flat spatula, not a round dowel, and we're going to pour one into the other, and we're going to simply mix. And it's important that you quickly scrape the sides and the bottom of the container to incorporate all the A and the B so that they get fully reacted. Doesn't take.
See how instantly it turned light, like you put cream into coffee? That was the cream time within a couple of seconds.
Too much. When the material starts to react, it'll form a nice even cream color, and you need to pour that into your mold. For this demonstration, we're just going to do a free rise block of foam so that you can actually see how this material expands. We'll pretty well got it mixed, and it's going to create just a little bit of heat on its own. Again, 72 degrees is the perfect temperature to start mixing that. It gives you about a minute or so of time to actually mix the foam and pour it into the mold. You got to be careful now not to put too much foam into a closed cavity mold, because it does create quite a bit of pressure on its own, and it could warp your mold. So now it's starting to come up, and actually to demonstrate this, we're just going to let it come up to kind of show you what we call free rise in this. So it comes out, it's going to expand, and within about 2 or 3 minutes, it's going to get to be full hardness. And we'll be able to actually pick this up, carve it, and show you how it's used. It's best not to get this on your hands, and I'm not wearing gloves, but you should wear gloves with this right now, because it loves to stick to human hands. That's about it. And you can see I only had about 500 milliliters of liquid, but you can get a sense of how much volume with this. Now, foam is sold in different densities, from very, very white cakes that are 1-to-1 volume.
All right, when when you do the lab, if you were doing it, I have, when I wrote the lab, I have the quantity, so this raises about 1 inch off the top of the cup. No, we don't want it going all over the place like that. Also, when we do it, I have you put a layer of special plastic paper, then on top of that, a few layers of a newspaper, because it's hard to get urethane foam once it hards off stuff, like a bench top of a lab, and you don't want that. And that's the urethane foam. Let's look at the lab. And notice I give you the cream time, the tack-free time, and was there an exotherm? Yes. All right, that's the first one. Next one, oh no, hang on, I gotta reboot my Word. Sorry about that. One of these days, I'm gonna figure out why the machine does that at times. All right, everybody see part 2 nylon? Now, nylon is an amide, a polyamide, where the repeating unit is an amide. Now here, usually do a diacid chloride. Now an acid chloride, and remember here is a carbonyl, is like a carboxylic acid, but it's much more reactive. And because this gives off HCl, you normally have a base here. And this forms nylon, which is a polymer. Now this is a neat one. In one beaker, you put the formulation I have here with the carbonyl chloride is the acid chloride with some dichloromethane, a solvent. In the B beaker, you put the diamine with some base you put in there, and you slowly pour the B into the A. And between the two, once you do that, in the beaker A, you'll see 2 layers. And at this layer right here, that's where the nylon, when the 2 chemicals come together. And what I have you do is we have a wire hook, you stick it in there. You catch that and you pull it up and you start pulling and you wrap that around a beaker and you can get a couple of yards of nylon. Now, since it's not purified, you can't use it at home, but it's really a lot of fun. And again, I'm sorry you're not doing it. And let's look at this video. And notice he's pouring it, the B into the A. The smoke is from some of the carbonyl chloride reacts with moisture. I hope everybody see YouTube on your screen right now, video. And now instead of a wire, he's using it. And see that white solid that's coming up? That's nylon. It's that fast. Now, I've never worked in industry. Now, I have you wrap it around a beaker so you can just keep on turning the beaker, not what he's doing. It's easier just to turn a beaker, and it goes on and on and on like the Energizer Bunny. And it's fun. Now, when we do this for the urethane, this sebacol chloride does not work well on your skin. And see how he's going on and on. And I'll let you look at the video at your own leisure later on if you'd like to look at it. And for this lab, what I do is I tell the students, when you start making nylon, call me over because I want to have fun watching you do it. And they do. And that's the lab. Now, the last one is a really fun lab, and you can do this one at home, actually. Now, boric acid or borate salts will, and here's an important reaction you should know. And if you take alcohol, 3 of them, you'll get, this is called a borate ester. And yes, I have 2 patents using borate esters, so I know about them. Now, if you take certain alcohols, you can make this whole ester very high molecular weight. And will it be soluble in water when it's high molecular weight? Well, I'm not going to give it away. Now, in this lab, I have you do 2 alcohols. One is isopropyl alcohol, and the other is polyvinyl alcohol. Actually, we use Elmer's glue. And Elmer's glue has this structure. This is polyvinyl alcohol, where N is on the order of about 500,000 to 1 million. And when you mix it with the boric acid and water, actually we use, instead of boric acid, sodium borate, which is 20-multene borax. With the isopropyl alcohol, you get a clear liquid. Here, you get a lot of cross-linking and big molecular weight. You get this gluey, slimy, white solid. And if you do it different ways, it can be different amounts of slimy. And that's what they use in the movies for monster slime. And let's take a look at the last video. After this commercial. Now they're doing a different than we do. We don't do it this exact, but
oozy slime, and it's so much fun to play with. First, we will begin by creating our slime activator. You use 1 cup of hot water with half a teaspoon of borax.
that's your boric
Mix
acid.
and stir it well so that you dissolve all the powder. Once you are done mixing, you can keep it to the side. If you prefer not to use the borax activator, you could also use contact lens solution that contains boric acid. Now we'll start our slime. I'm using 1 part of glue, so 1 bottle of Elmer's PVA glue, and I'm going to mix it with warm water.
We don't even mix it with the water. We want
Warm water
really good
into
slime.
the glue bottle.
In the lab, we have a gallon bottle of that.
And I'm going to shake it. That will help spread the leftover glue inside. And open it up and add it to your mixture. Now just go ahead and mix it all together so that you don't end up with any clumps. You want a nice smooth mixture. I tend to keep on hand a bunch of ice cream sticks because they're the easiest to clean up afterwards and they do a great job of mixing.
That's why I don't use.
Then you will add your food color.
We don't use
I
food
choose to
coloring
use food
because
color
we don't
just
want
because I like how vibrant
you to
the
get it
colors
on your
come out.
clothes or your
You just need one
skin.
drop. I'm going today with a purple color. For some reason, it's looking a bit bluish. I chose purple because we currently have a million different slimes at home. So we've got a butter slime that's yellow. We have 2 fluffy slimes that are pink and blue. You can find the recipes and video tutorials by clicking one of the links. Keep mixing until you don't have any streaks left over.
Again, we don't use the food color.
Now your borax mixture would have had time to dissolve. Make sure that you give it a good mix before you start adding it in. This is really important that you add it in really slowly because this is sort of the part that's going to make or break your slime. So I tend to go and add in a teaspoon at a time and then I mix. And then I can add another teaspoon at a time and mix.
Is that cool? I love it. Isn't chemistry, organic chemistry, wonderful?
You will see that it starts to sticking together. As I raise my spoon, I'll show you. Yeah, see? And I think it's better when you are adding in the borax that you don't just add it to one place because then just that area is a much better way. Please make sure to subscribe because we have so many fun ideas. Shaving cream, smell all over you. 2 teaspoons of borax. I probably added I think I added 6 teaspoons and I could tell from the consistency with my hands that it was still a little bit too sticky. So I went ahead and added 1 more, mixed again. And then now
when the students do it, we just take some Elmer's glue, put in some solution of the borax and I have the students mix it and you get this gooey, slimy monster slime. And with the isopropyl alcohol and the borax, it stays a clear solution. And remember the reaction I showed you right here. And when R is the Elmer's glue, it's quite large and higher molecular weight. And here are the questions. And with that, I'm done today. Thank you for letting me go a little longer than normal because this way we're caught up. Don't forget, office hour tonight if you need help, 8:00 p.m. I'll stay late if anybody needs me late. And also, don't forget, tomorrow will be test number 3. I'll send out the password for that right after class. And before you run away, let's do one thing real quick. So I believe we had a problem last time and I think I solved it, but let's just check. I'm going to go to the student view. Yep, you should all see D2L. I'm going to go to the assignments. And notice it's available for you to download now. And that's test number 3. I have the PDF file. I included here, which I didn't do in the past, and I should have, in case you don't have a scanner. A good way is the CAM scanner. Don't buy the expensive one. Just get the free version, or you can read the instructions. And with that, let me first log off, switch back to here. Log off. Do this and say Have a nice rest of the day. Gain gesund. Goodbye. Remember, gain gesund. Be healthy. Goodbye. I'll see you tomorrow. Bye now.